Okay, so welcome back, and this is the last in this week's videos looking at isomerism. So in the first couple of videos we looked at a recap of the different types of isomerism which covered so far in the course and looking at geometric. We also looked at the new type of isomerism, optical isomerism, and we discovered that optical isomers are molecules which have non-superimposable mirror images. One of the easiest ways to tell this is to look for a chiral carbon. That's a carbon with 4 different groups attached to it. If it has a chiral carbon, it's going to be an optical isomer. In this video, we're going to have a look at how you test for optical isomers and why they're important, especially in biochemistry. Because optical isomers have 2 key differences in their functions. Firstly, it is the difference in their interactions with plane polarized light, but more importantly, from a biochemistry viewpoint, is their different interactions with other chiral molecules. So this can lead to some quite devastating effects, for example, thalidomide, which we're going to talk about later. Okay, so we're in your notes now and we're looking at page 6, how we can distinguish between optical isomers. So one way to distinguish them is to bring them into contact with another chiral compound. Living organisms have enzymes which can detect the shape of the molecules very, very accurately and can tell the difference between the 2 optical isomers. So, for example, oranges and lemons smell different. Caraway and spearmint taste and smell different. Although they're the same molecules, because they're optical isomers of each other, they have a different interaction with the chiral molecules of your nose. However, when we're using conventional chemistry or physics, it's quite difficult to distinguish between the 2 isomers, because they have identical physical and chemical properties. One key property that they have, however, is their effect on plane polarized light, and that's how we use or we test for them in the lab. So optical isomers will rotate, and that again is a key word, not reflect, not refract, not anything else, rotate the plane of plane polarized light. So each isomer will rotate the light by the same amount, but in the opposite direction. So if one isomer rotates it by 15 degrees to the right from the normal, the other will rotate it by the same amount, but in the opposite direction. Okay, so what do we mean by plane polarized light? So unpolarized light is vibrating in all planes. We pass it through a polarizer, which is a little bit like a sieve. So we get polarized light, light that is only vibrating in one plane. We can then pass this through our sample, and you will see that the plane of that light is rotated from the normal if we have an optical isomer. Okay, so on page 7 you can read about 2 different activities. One is looking at honey and the optical rotations of natural sugars, and the second is looking at ibuprofen and its optical activity. So ibuprofen exists as a pair of optical isomers. So on the skeletal molecule at the bottom, we have our chiral carbon, which is that carbon there. You've got to remember this is skeletal, so there'll be a hydrogen there as well. So I have 1, 2, 3, 4 different groups. So I have an optical isomer. So I have 2 versions of ibuprofen. We call them R and S. Okay. Now the S version in this case is what we call optically active, and the R version is non-active. Fortunately, our R version doesn't have any nasty side effects, and it's quite difficult and quite expensive to separate out the 2 optical isomers, so we tend to give this as a mixture of both the R and the S. And in fact, your body quite often turns quite a lot of the R's into the S version. So you get a higher dose. For some drugs, it's very important that we do separate out the isomers and we only give one isomer to the patient. A good example of this was the thalidomide scandal, where you had 2 isomers. One version combated morning sickness, but the second version, the, if you like, evil twin, stopped limb development in growing fetuses, and caused severe birth defects, children being born without arms or without legs. So it's quite important that we distinguish between the optical isomers. So we give ibuprofen as a mixture, and we call that mixture a racemic mixture. And a racemic mixture is a solution which contains equal amounts, equal number of moles of both optical isomers. So, with that in mind, would you expect a racemic mixture to be optically active? In other words, to rotate the plane of plane polarized light? Well, the answer here is very simple. No, we would not expect it to show optical activity. The reason for that is these rotations. So if we think about what's happening, we've got equal amounts of both enantiomers, both optical isomers. One will rotate in one direction. The other will rotate by the same amount in the opposite direction. So you're going to come back to where you started. So in other words, you can't see the optical activity. It's still rotating the plane of plane polarized light, but those two rotations are cancelling out. So explaining that, we say that one isomer will rotate the plane of plane polarized light. The other will rotate by the same amount, but in the opposite. And be careful you don't use words like different. It's got to be opposite. Okay? But in the opposite direction. Therefore, optical rotations cancel out. As I said, one will rotate it by a certain amount that way, the other will rotate it by exactly the same amount in the opposite direction. So basically you will end up back where you started from. Okay, now if at home you can find an orange and a lemon, you can do this little experiment yourself. But they both contain a compound called limonene. They smell different because they interact differently with the chiral receptors in your nose. So they've got chiral carbons at the bottom of the ring, and that's why oranges smell like oranges and lemons smell like lemons, because they interact differently with the chiral molecules in your nose. So on the top of the next page, we have two more optical isomers, R and S carvone. And R and S carvone have, again, a chiral carbon, and it is here. You should be able to draw this one. Remember, you've got that kind of mirror between the two, so they're mirror images of each other. And the S version smells like caraway seeds, and the R version smells of spearmint. Some people can't detect the difference between these two because they lack a particular gene responsible for this receptor. Other people can smell one but not the other. But most people, probably about 90–95% of the population, should be able to distinguish between these two just by smell. So biologists should recognise this at the bottom of page 9 as an amino acid. So we have our carbon with what we would call an amine group, and you'll sometimes see it listed as an amino group, a carboxylic acid functional group, a hydrogen, and this R group. And that's what makes the different amino acids. They change by having various groups onto their R groups. Now, if you take a molecule like glycine, which is the simplest of the amino acid, it's the only amino acid which is not optically active. All other amino acids are optically active because as long as this R group is different from the other three, then you will have 4 different groups. You will have a chiral carbon, and therefore you will have non-superimposable mirror images. However, in this case, this carbon, we've got no chiral carbon, as my alpha carbon, my C, has 2 hydrogens. So there's no chiral carbon, therefore the molecule has a superimposable mirror image. Okay, all the other amino acids, so aniline, cysteine, tyrosine, all have at least one chiral center because they have a different R group. So this is the R group here, this is my R group here, and this is my R group here. So they all have a different R group, and that's what gives them the chiral carbon. Okay, so we're on the last page of the notes for this week, and we're looking just at this little true-false statement. So what I'd like you to do is pause the video at this stage and go through those and just tick whether or not they're true or false. Okay, hopefully you've had a chance to do that, so I'm just going to go through these. So, firstly, racemates contain 2 enantiomers in equal numbers. Well, yes, that's true. That's the definition of a racemic mixture, equal amounts of both enantiomers. The synthesis of a single optical isomer rather than racemates is less expensive. That's false. It's actually more expensive because it's quite difficult to make only one isomer. Chiral molecules produced naturally tend to be a racemic mixture. That's false. Because it's produced by natural chiral molecules, they tend to also produce other chiral molecules. 2 enantiomers have identical properties when taken as a medicine. That's false. If 2 enantiomers have different effects on the human body, one will be inactive and do nothing. Again, that is false. We've seen that with thalidomide, where one drug was effective and the other drug was ineffective for morning sickness, but shut down limb development in a growing fetus. Chiral drugs which are administered as only one enantiomer normally have an increased effect and reduced side effects. That is true. It's quite often the other version of the drug which causes a lot of the side effects. Naturally occurring chiral molecules can be used as a starting material, or yes they can, and we can use chiral catalysts to confer chirality, and in fact the 2001 Nobel Prize was given for the development of chiral catalysts. Okay, so that just finishes this video for today, and this finishes the section for this week. So this week we've looked at isomerism, and we've been able to identify optical isomers, and we've talked a bit about racemic mixtures and their biochemical effect. Next week we're going to go on and look at the role of optical isomers in mechanisms, and we're going to be looking back at the mechanism we did in your carbonyl pack, where we looked at the nucleophilic addition mechanism. So we're going to look at that and a couple of others, and we're going to finish off with some exam questions at the end. So until then, take care, stay safe, speak to you soon. Bye bye.